And I'm gonna start sharing my screen. Now, cool. And as I always like to start this sort of reviewing what you know and having a conversation first before we look at any code. Um, so, what does anyone know about linked list? Just unmute yourself um, and shout out something.
Linked list is a node.
Okay. I'm gonna fix that a little bit and say that a linked list is made of nodes,
It's made of them.
right? It's not just a node. Cool. Made out of nodes. Cool. Anything else?
It has a tail and head.
It can have a tail. Can have a tail and head. Cool. What else? Joanne, one thing you know about linked list?
They have pointers.
They let's say they involve pointers. Involve. Is that right?
Yeah.
They involve pointers, and we'll see. We can talk about that. Actually, what is one thing you might remember about linked list? I'm not sure if she is with us at the moment. But what anyone else wants to add anything?
A linked list contains two things. It contains the data is stored, and it also contains the link to the next node.
Okay, so that will be the node. The node contains those two pieces of information,
Yeah.
not necessarily the linked list.
Oh,
The linked list is sort of like is the idea, and it's gonna be sort of a container class that we'll have that keeps track of the tail and the head. And the node is has two properties: one for storing the data and for the next. Yes.
You can say that it's like a linear data.
Is as a linear data structure. What do you think that means? That is interesting.
grows. It means it grows with the data, right? The memory grows with the.
But not necessarily, because we could say all data structures that you're adding stuff to it will grow. But what do we like? This linear part is kind of interesting. I'm glad you brought that up.
It's like
Siham.
an array and it has a limit, no? When we store the data.
It doesn't have a limit. It doesn't have a limit.
I don't know, maybe like I'm talking about if the way how it stores.
Yeah, yeah. I mean, yes. That linear means that it begins at some place and it finishes at some other. Um, let's put it in contrast with nonlinear data structures. Does anybody know of any nonlinear data structure?
You said non-linear.
Yes, nonlinear.
Uh, Sorting.
But sorting is an algorithm. Uh, I'm talking about data structures.
A non-linear data structure.
That's right. So that's okay. I remember when I saw this for the first time as well. I was like, I don't know what that means. But a nonlinear data structure example is a tree. Um, a tree is a nonlinear data structure because a tree looks like this.
Mm-hmm.
Is that when you said the linear structure, that's mean like it's sorted, no?
Yes, that is right as well. Let's do that sorted. It's actually not sorted. Let's is order.
Yeah. What's the difference between order and sorted?
Order, we can say that there is a sequence, that there is the first thing and then the next thing and then the next thing. But sorted means more like, oh, the data is in a very specific order. That like if it's numbers, then they could be sorted least to or less to greater, least to greater, and so on, or vice versa. Order just means that it follows a sequence.
Okay.
So that's a very good observation. And a tree is a nonlinear data structure because you know where it starts, right? You know that it starts here, but where does the tree end, right? It has multiple ends. It ends here, and it ends here, and it ends here, right? So then, yeah, go ahead, Henry.
Oh, question. A hash map is another example of that or no?
A hash map is a nonlinear data structure as well, because we don't really know where it starts and where it ends, and you might recall that hash tables or objects are not good at keeping track of the order in which things are, right? So that's why this is important. Linear data structure means order. What's another linear data structure now that with that context? What's another multiple ends?
Oh, a stack.
That's right. You know where the stack starts and you know where it ends, and it is in the order of insertion. And then what are some others?
Queue.
Queue, that's right. One more.
Array.
The array, the most basic one. The array is a linear data structure. Others like this is a tree. I was thinking that maybe maybe it could be the next lesson. I want us to talk about graphs, and a tree is a graph. But a graph looks more like it depends on a graph could look more like this. You know, it's just nodes that are connected, and it's not a tree. But so a tree is a type of graph. This will be another non-linear data structure. Cool. And just also sort of on that same vein of linear data structure, we know that we can start at the beginning and the end at some point. But in the tree, we know where to start, but depending on where we want to end, we will need to pick a different traversal algorithm, depth first or breadth first. Because of that, there is not that order in which things go. Yeah. Any questions or thoughts on that? Let me put this here as also non-linear. Data structure. Cool. That was good there. I think that is most of it. Now, let's think about why linked list. Does anybody want to take a shot at that? Like, why do linked lists exist?
All I remember is that the reason why we would use linked list is because there isn't like a fixed memory as opposed to like when you use an array. With linked list, you could just also use O of one notate O of n. It's constant.
Wait, so let's say you said I think 2 points there that I want to make sure I capture correctly. The first one was some comparison with array. Can you repeat that one?
Yeah. So with an array, with other like programming languages, array has a fixed memory. So for example, when you're doing like C++, you have to like tell, like you have to give the array size, and it's fixed. So it can go no bigger than that. That's one plus of having a linked list. So when that's the first point that I was bringing.
Definitely.
The second point is that unlike an array where it would like run in linear, with linked list it tends to run in constant time.
Okay, but then there we have to clarify the what specific operations run in linear time and what specific operations run in constant time. So let me back up there a little bit. So yes, the first point, very important, the dynamic size nature of linked list. And just to put a visual on that, this is what an array will look like in memory. Oh, where did my lesson go? Linked. Linked list. So this is what an array will look like in memory. If we could look at the memory, let's say we have three strings in that space memory. When you, as Henry mentioned, in other programming languages, when you create an array, you have to specify what size you want the array to be. You want 3 slots, 4 slots, and you also need to actually specify what size are the things you're storing inside of the array, so that the computer can allocate enough space. And an array is fast because the spaces in memory for the array are contiguous physical spaces. So there's one right after the next, right next to the others. And that's what makes arrays fast at index, for example. Now, with the problem that linked list come to solve is, well, I guess like in here, what if we wanted to add something to this array, right? This array, there is no more space there in memory. That the next space is being utilized by something else. It could be Chrome, it could be a music app you're using, it could be Slack, any other thing that has stuff in memory could be there. So if we want to add another thing here, what happens in JavaScript, we talked about this like I think 2 sessions before with the dynamic array. What happens in JavaScript under the hood is you can push, let's say push breakfast to this array. And what JavaScript will do is it will locate some other place in memory 4 spaces. I will actually locate double the current size. So if it's currently 3 spaces, it will search the memory to see where are there 6 contiguous spaces. And then it will move the array there and add the element at the end of it. But then that move from one location of memory to the other location of memory, that will be in linear time because we have to move one element at a time, right? Now, that's the problem that linked lists come to solve, where each node can live in its own slot in memory and just store. It literally stores in the next property, it will store the address where the next element is. And by the address, by storing the address of where the next element is, then we can say the list starts here, and we follow in the links, we can get to the end of the list. And then the list physically in memory is not next to each other, but they're connected through the next property of these nodes. So if I want to add brunch, brunch is already there. If I want to add like breakfast, then I could use this 10th slot here and just say, if I can actually annotate here. Let's say I want to add breakfast. I could just add it to that slot, and then T is the last thing. Then and T, I make sure that I point the next of T to that, and so on. the memory management and where the memory is created is something that we don't care about. That happens for us all the time. But conceptually, that's what will happen. When we create a variable, a space of memory is allocated. We don't even care where it is. And when we connect, when we say like whatever node is holding T, that next, the node that is holding breakfast, then we're sort of doing that line there. And in this case, then you have much more flexibility. This is why linked list came to be. Because the constraint of arrays is that you have to have contiguous space in memory. But with a linked list, that space doesn't have to be contiguous. And this is like all as a, if you haven't noticed already, and this is, I think, a point that I keep mentioning, how everything we do in data structure and algorithm is always a trade-off. And that trade-off is generally space for time or time for space. You can either make, if you want to make your algorithm faster, generally you need to use some extra space. If you want to have your algorithm use less space, optimize it in space, then it's likely going to take more time. And in that preference, sort of a side note there is that computers nowadays have good amounts of memory, and we prioritize gaining in time and maybe using some extra space than the opposite. And it's also kind of interesting as well that what just came to mind is like, like in life, you can get more space, but you can't get more time. And that's also sort of what we prioritize here, time. But the trade-off here is then the trade-off, if we think about it with arrays and linked lists, is with an array, I could just say, array at index 3, and that happens in constant time, because literally, well, we talked about this in the previous session. They use the array to locate 3 is just using some simple math to do the multiplication of where the address where the array starts times 3, whatever size the element is, and then it is able to find that slot in memory in constant time. Here, once we have a linked list, we lose that constant time access. If we want to find out T, for example, we can't index like we do in an array. We're gonna need to loop over the list until we find T. So that's a trade-off there that we're doing, where in the array we might be using we need contiguous space, and we might be wasting some space in the array, but going to an index is in constant time. With a linked list, we're not wasting any space. There's no empty slots on the linked list. And we have the flexibility of not needed to have contiguous space in memory, but to gain on those flexibilities, we lose on the index, being able to access something in the middle of the linked list, quickly. That will be a linear operation. And then the point of this lesson is to just review some of those concepts that at some point we have seen. Okay, any questions or thoughts up until this point?
Nope.
Cool. Okay, so this is how we can sort of visualize a linked list. I'm sure you're familiar with this visualization. We have one node that points to another node through its next. In this case, 1 that points to another node through its next. And in memory, that could be all over the place. But what matters is that they are linked. Cool. So this was a point that Henry mentioned. So we need to represent these nodes, and and this is true, like this is the way we do it in JavaScript. We just create a class node, which is, as I like to say, a blueprint for objects. And then you just create objects that have two properties, a value and a next value. And that is the way that I have seen most nodes, even in other programming languages, being implemented with a hash table, a map, a dictionary. In ours, it's just an object that has two properties. I think C uses something called struct, which is sort of a similar idea. And we store two pieces of information. We store well, what it is that we want to hold on to, what data do we want, and we hold a reference to the next node. And that is then how we will be able to connect or traverse the linked list. I think someone just joined. Yeah. Cool. Okay, so a node by itself is just an object. It's just a simple object that has two properties, like any other object that you're familiar with. And by itself, it can't do much. But if we couple it with some ideas, then we can have a list. At any point, feel free to interrupt me with any questions, etc. Okay, so the node by itself can't do anything, but then we can start connecting them. Well, we can create some nodes. This is, so we had done a review of linked list, but I think this was like before we were sort of in the employment team. And I think I did that with the 6.2 fellows, where we basically build a linked list manually, which we're gonna see here. And then after we're gonna move to how to have some helper methods to build a linked list. But here we basically can create nodes like we create any other objects. And in the constructor, we pass in the data that we want. So if we visualize this, well, also, I think I might have, I think I had this part here that I wanted us to look at, which I think I also have here. Give me 1 sec. Yes, here. These were some graphics that I had drawn from last time that can help us here. Put this full screen. Oh, so this was like another visual idea where you can think of it as, you know, a node is just an object, and we could visualize that as a box that has a compartment for the value and a compartment for keeping a reference to a next. And we'll see, you know, with that analogy, what that could look like. And we could, you know, in our mind, we could see that as something that just holds two compartments. So we could create the nodes by just declaring variables and invoking the new constructor for a node. And then that will create these node objects. But by themselves, they don't do anything. What we could do next is, what we could do next is then connect those nodes. We can say n1.next is equal to n2, and that connects n1 to n2, which is 3 in this example, to 5. And then we can say n2, which is holding the value 5, that next is equal to n3, and that connects that next compartment to n3 node, whose value is 1. And then we can do n3.next equal n4, and so on and so forth. And in this case, then at this point, we can say we have a linked list, because a linked list is just linked nodes, right? A linked list is just linked nodes. And then this is the linked list that you're going to deal with most in LeetCode and in interview questions. They give you a linked list that was built like this, and they give you the head of that linked list, and that's all. That's all they will give you. And then they ask you to find an element in the linked list, or to find if the linked list has a cycle, and so on and so forth. That the linked list with a cycle is a very common problem. Has anybody come across that one, either in an interview or coding challenge or elsewhere?
Repeat that question again. Which question?
Yeah, if detecting if a linked list has a cycle.
Oh yeah, with 2 pointers. Yep.
Okay, the two pointers approach. I think it's so Henry and Joanne, Siham, Shia, or Aranza. Have you ever come across that one?
No, I haven't.
Okay,
Yes, well, and Litko.
I see. Cool. Yeah, that one is a very common one. That is interesting. But the point is that most of those problems, this is the linked list that they'll give you. They'll give you N1, and that's your head, and then you have to do the rest. And we will see what we'll build after this is a linked list class to keep track of the head and the tail, and so on. And I wanted to, yeah, like if we follow this visualization with thinking of these nodes as boxes, we could say that the first box that is holding number 3, that node or that next reference could be sort of like the string coming out of that box, going to the next box, which is the one that's holding the value 5, and that has some other string going to the next box, which is the box with value 1, which is not even here in this drawing, inside of the picture. And then that is pointing through a reference, in this case, the analogy is a string, to the last node with value of 6. And these boxes can be anywhere in memory, and in the analogy, anywhere in the room. But you'll still be able to go visit all of them because you're following the references, you're following the strings. So even if you're getting just the head, if you only know where the first box is, you're still able to get to the end by following the links. Cool. Let's go back here. Let's go back here and okay. So this linked list, this could make a linked list already if we connect the nodes. That is already a linked list. So that is cool, but it's kind of tedious to have to create the nodes in this way and then connect them manually. It's not a very dynamic linked list implementation, right? It's like you could think of it as kind of like hard-coded almost, where this linked list is 3. Once we run this, like how can we add one more element without having to just write another one of these lines and another one of these lines, right? So for that, what we use is then creating a linked list class that acts as a container class for these nodes, that then has methods to easily insert an element, and to easily remove elements, easily find elements, and stuff like that. That is just helpful, and can make the developer life easier, as well as the data structure just dynamic. Yeah. Cool. And I guess like just one more example here is like, let's say we're building a linked list to keep track of a music playlist, for example. If we code it like this, let's say, then that playlist will only have 3 songs in it. But then how do you allow the user to add more songs? We can't unless we write a function that the user can call when they click on add music to add song to the linked list, or add this song to the playlist. So those are some of the problems that the linked list or the container class comes to alleviate. So the linked list we'll just, well, okay, wait, actually, hold on. Before we go into here, yeah, let's actually, I want us to do an exercise. So let me stop sharing here for a second. I'm gonna send you a link to a REPL. Oops. And I don't think so let me share this link here in the chat. And we're gonna do, before we look at the linked list implementation. So what I want you to do is go on that link, and that has a simple linked list built manually by hand, which is actually the same as has the same numbers as the boxes visualization. And what I want you to do is to write a function called contains, that given a number, returns true or false whether that number is part of the linked list or not. So let me share my screen here again, just to see the signature of the function. So I want you to have a function called contains that receives the head node, or I'm just gonna say node of a linked list, and it should return true or false. Also, let's say node and a target. It should return true or false whether, I don't know how to spell whether. So like that? No. Like that.
No H. On the first H, yeah. Wait.
No, it has an H.
It has an H, my bad.
Oh, double H?
You good.
Cool.
Yeah.
There's, I think this was, I was talking to Sian about some words that are difficult to pronounce, and some words that are also difficult for me to spell out, even though I know what they mean. I think that's some, what's it called? Dyslexia, I think. Yeah.
Don't do that. I don't have that.
I don't think I use the right term. Something else, but it happens often.
Like, you do that in Spanish too, or no?
Yes, I do.
Oh, okay. So,
where sometimes I forget the order in which the letters go.
Oh, okay. It's probably dyslexia. Okay, cool.
I do it often.
Yeah. Anyway, it returns true or false whether whether the target is found in the linked list. So just one more time, your job is to write a function called contains that takes in the head node. So I'm gonna call this like this: contains n1, and I'm gonna search for 1, and this should return true. I'm gonna call it like that and search for 100, and this should return false. Console log. Oops. Oh no. Console.log. Cool. Okay, give me a thumbs up if it's clear what the goal is. Maybe not clear how it's gonna get there, but clear what the goal is. Okay, I see physical thumbs up and virtual thumbs ups. Awesome. Cool. So does anyone would like to share the screen? It doesn't matter if it's incomplete. Let's take a look at it.
I mean, I don't mind sharing, but it's like it's all over the place. So bear with me.
I see.
Give me a second. Okay.
Okay. Let's take a look.
Can you hear? Can you see me? Can you
Yep.
see the screen? Okay. So I thought to set a current for the node to keep track of the node, right?
That's a good idea.
While current, oh, wait. I think hold on. Then I wasn't sure if I should say while current exists or while there's a current dot next so that it knows when to go to the end. But I put current dot next.
Yeah.
It knows that when there's not a current dot next and it reaches, then you're at the end, then it'll break out of the loop.
In this case, it will be better if it's just current, so
Okay.
that we actually look at the very last one.
Okay, gotcha. Because then I was like, how do I look at the last one? So boom. Okay, so leave it as current. So while current, then I said if current dot val is not equal to target, return false. Originally, I said if current dot val is equal to target, return true. But then I didn't know where I would implement line 26 that'll set the current to the next node. So
Okay.
I did it outside of the condition, but maybe I should have did it inside the condition.
So outside is the right place here.
Okay.
And the condition should be the opposite, the way that you had it before. If it's equal to the target, let's return true. Otherwise, also, because if we leave it the way that you had it, then if it looks at the first element and the first element is not the one, then it's just gonna stop there and it's not gonna keep looking on the rest.
Right.
Right. So then here we want to return false. Otherwise, this is pretty much it. There's one thing though that I didn't understand, which is line 21. You're putting the node instead of an array. That wouldn't be necessary.
Okay, because I couldn't remember like when I thought, I can't recall, but I feel like I've done before where I was keeping track, especially dealing with like a linked list or maybe like a binary tree or something. I set the node equal to current, but I had it inside of the brackets. I don't know why, but I thought to do it with the brackets.
See, yes, that might have been breadth first search on a binary tree.
Oh yeah, okay. I see. Okay, so no brackets.
Awesome.
Right,
Let's try it out.
Yes.
Awesome. True and false. Okay, questions from peers. Jonathan, Joanne, Henry, Aranza, Siham.
I did mine almost like the same way, but except I put in my while loop, I put the node.
Okay.
I'm only getting the true, but I'm not getting the false. I don't know if it's because my computer is extremely slow or not.
But do you have everything exactly the same? There's only one line different, which is like 21.
Yeah, more or less, yeah.
Yeah, 26.
26 is important, and 28 as well.
Yeah, I do have 26.
Okay. Let's take a look at what you have. Yeah. Thank you, Ashia. That was great.
This one. Right.
Cool. Let's see. Does anyone see something weird?
Yes. So she's using both node and current node as a variable. So because you have line 21 as your node, you'd want to say while current node instead of saying like if you use while node, then line 26 would have to be node equals to node dot next.
So it seems like it just gets stuck on the first one for some reason. Can we take a look at the and 1 next and 2 and 2 next and 3 and 3 next and 4? Oh, I think, yeah, let's try to run it again.
And also I keep getting like the squiggly lines. And I already checked on my my indentations and all my curly brackets are there.
Yeah, that's weird. Can you scroll up a little bit?
Maybe by using the semicolons on the end of the lines, because sometimes with like the line, it doesn't read the next line if there's no semicolon.
Actually, that doesn't really matter in JavaScript. There are some other languages that are very finicky about that, but in JavaScript it shouldn't really matter. Maybe try. I think your computer might be acting up. Try to refresh the page. Oh, it might have been also. You know what? I think it's, yeah. This sometimes happens with REPL, where you get an infinite loop, which is what you were getting when you were not using current node and you were using node, or that confusion. Whenever this is like a problem with REPL, whenever you get an infinite loop, then REPL starts behaving weird. Maybe it should be fine now. Let's find out.
Oh my gosh.
Or I just seen something. Maybe on line 26, it should be current node equals to current node dot next.
Oh, there we go.
Oh.
That's a good catch, Ashia. Yes.
All right, thank you.
So this is we're getting an infinite loop here.
Okay, now it works.
Awesome. Thank you. Really good catch. Okay, so before you stop sharing, Siham and Anansa, does this make sense?
Yes, I got it to work.
Awesome.
I
Cool.
did the same thing, just like I put like while node, and I put just node that value equal to target.
Okay.
And node equal to the node next. That's
Awesome.
I didn't change anything.
Mm-hmm. Awesome. So this is a linked list traversal. You just wrote a linked list traversal algorithm that traverses the linked list. Does anyone want to try to say what the time complexity of this will be?
Of n.
Okay, where what is n?
Linear.
That's right. But I always, yeah.
So it's the size of the linked list.
That's correct. The length of the linked list or the size of the linked list, how many nodes there are in the linked list, exactly. It's always good to state what is n when you're talking about O of n. Cool, yes, linear O of n. Okay, so this is cool. Now I'm gonna switch a little bit, which you're gonna use with you're gonna use the same traversal algorithm, but now I want you to write a function or modify this one that that prints the linked list in this format. I'm gonna paste it here in the chat because I don't think I don't need to share my screen for that. But I want you to write a function called print that prints that same linked list in this format. Cool. So write another function. It's going to be very similar to contains that at the end should console log the list in this format with like the number and then an arrow, the next number, and so on and so forth. Let's take 5 minutes for that.
Would that be like a sort for the linked list? Like, can you sort with the linked list?
The answer is yes, but this would be sorting the linked list. Yeah. This would be just printing it.
Oh,
Sorry. I guess like the example I gave was sorted. Sorry. But for the linked list that we had, I think the output should be for the linked list that we have, the output will be 3, 1, 5. No, 5. Yes, it should be like this for the linked list that we currently have.
okay.
Are we using the same function or are we creating another one?
I would say create another one.
Okay.
Mhm. Hey, Ferris.
Hello.
It's good to see
Hi.
you.
Hi. Same to you.
Oh, I forgot to start the timer, but yeah, it's the 4 minutes.
Okay. Then the third iteration, value is 1. Next node, wait a second. It gets a little crazy. Hold on.
But next node is right. Next node is 6.
6, okay.
So keep going after that.
Then if we do the last iteration, the node value is 6. The next is null.
Mm-hmm.
So
And then after that, you see another iteration.
Yeah.
the iteration 7.
Mm-hmm.
Okay. Oh, okay. So it's doing one extra iteration once it adds. Okay.
Mm-hmm.
So, all right. So if it's doing one extra iteration, then it's adding it on to the linked list, but it's not stopping. So,
Yeah, it stops one iteration over. Yeah.
so maybe it's my while condition.
So it could be so you just may realize that this could be solved this way that you're doing it, just with one small tweak, or the other way, which is something to do with the while condition. But I wanted to bring your attention to this fact that your iteration here, and then what you get here is what do we call this right side? This here.
We get a object.
That's right. It's an object. It's an object. Oh, for some reason you have a previous thing, but I guess that's something you added at some point.
Oh, because I think because of the what you would call it, the class the
Got it.
the
Okay.
constructor. Yeah.
Got it. Okay. We could get rid of that since we're not using that previous one.
Okay.
Was that in the one that I shared?
Yeah.
Oh, yes, I didn't realize. Sorry about that. That will be for a double linked list. If we were building a double linked list, that will be used. Okay, so just run it again.
Yeah. Okay, better.
So we get a little bit less output, yes. But then the point that I want to make is this is an object, and is more explicitly is a node, right? It's a node object. And that's what we're seeing in iteration. But what are we getting here when we expect to see another node object with the value of 7, but we just see 7?
Where it's an integer.
Mm-hmm. So how do we make 7 a node?
We gotta say new node.
Yes.
Okay.
So we could do that in line 55.
Okay. So would it be let new node? Would I initialize it?
Yeah, you can do that.
Let new node equal to, wait a second. Let new node.
Equal was good.
Okay, equal to.
Then there's a keyword here.
New.
That's the join.
New. Oh, new.
Mm-hmm.
And then node.
New node. Oh, okay. New node.
Mm-hmm.
And then like that, right?
And then you need to put something in the parentheses, which is the value you want the node to hold.
Okay. So then the node that next would, instead of saying value, would say new node.
Mm-hmm.
Okay.
Now let's take a look.
Okay. Oh, stop.
So we got, I actually suspected this, but did not think too much about it. We're getting an infinite loop, it looks like, right?
Yeah.
Then why is that?
It's.
Let's go see him.
What is funny, I got the last number. I skipped a number before.
Ah, I see.
Nice.
Um,
Fluffy.
so we're getting actually also Joan, I think you were gonna say something as well.
Maybe
No,
I'm sorry.
go ahead, Sam.
No. Go ahead. I'm sorry.
Yeah. I was just gonna say that does it have anything to do with the fact that we're doing the new node inside the loop?
Oh,
Mm,
I don't know.
it's got to do is that's close. It's got to do with the fact that we're appending inside of the loop, that we're adding the node at the end. Um, so what happens is that the linked list is what's the last node in the linked list? 6.
yeah.
Um, and then we arrive at the there is no next. Imagine this is only just the end, so I don't want to draw the entire thing. It arrives at the end and it's checked that the next is null. The next is null, right? There is no next of 6. Then it creates a new node that I'm going to represent with a circle, and then it puts 7 inside. And then it does, okay, node that next. Oh no, and then that's it. But then it does node equal node dot next. But node was pointing to this, right? Node was pointing to the 6. And this is something that we alluded at the beginning, where we're using sort of pointers. Here we can say node is a pointer to the node with value 6. So node with value 6. Let me restart there. So the current node is node with value 6. We check if there is no next, which is line 54. There is no next, so we create a new node, which I'm going to represent with a circle. We put the 7 inside, and then we say that's it. And then after that, well, we will console log in the value here, but after that, we're going to move on to the node next, which then moves the pointer from 6
Oh.
to 7.
And because I just added it.
Mm-hmm.
Okay.
And then that does the same thing, which will add another 7 here, which will add another 7 here. In fact, our linked list is growing with 7s until our computer runs out of memory at some point.
So should we reset the end to null, that we can stop the loop?
So we won't, because the 7 next is already null. So the way in which we could approach this is we could break from the loop if we did an append. So like in line 50, after line 57, you could say break. And if you say break, then the while loop will stop there. And this is one way in which we could solve this.
Okay.
So we can say break after we did what we wanted to do. And in this case, like we notice that bug that it just keeps adding 7.
Mm-hmm.
The other approach will be something you alluded to, Ashia, which is instead of checking if node, we could check if node that next. Let me try to draw it here. Oh, this is still drawing. Oh, I think. So, okay, so we check, but then we wouldn't do the append inside of the loop. We'll do the append all the way at the end, outside of the loop. So line 50, 67 and 68 go outside of the loop. And then we wouldn't need the if statement altogether, 66 to 68. Let's try append 2. Maybe try append 8.
Oh, okay.
Okay, does it make sense how this works though?
A little. So okay, so while no.next exists, we want to continue through the loop. So we want to look at the next node. So that's why we do node equals node.next. Otherwise, if node.next is null, that means we break out of our while loop and when we establish a new node that will take in the value that we want to add, and then node.next is going to equal the new node.
The key here is that this ends one. Oh, this is a bit hard to see. Actually, do you think you can move the terminal to the right a bit more so that I can draw on the white part? Awesome, thank you. So we have 6. Let's say for appending 7, which is just the same thing. So here, once we start here, this is node, and then you're checking if node.next is a thing. In this case, node.next is 5, which is a thing. Then we just move on to the next node. We just say node equal node.next. So now we moved on to 5. And then here we're checking if node.next is a thing before we move on to that thing. So in this case, node.next is 1, or is the node with value 1, which is a thing. Then we move on to that node there, 5. Fixing that 5 there. And then here we check if node.next is a thing. It is, which is 6. So we move on to that node. At this point, we check if node.next is a thing. Node.next here is null. So it's not a thing, which then creates a new node. And then it uses the current node, that next, to append that new node. So that will create a new node, let's say 7. And then say current node, which is pointing to 6, that next equal to that new node, 7.
I think I have to remember that you can work the positives in a while statement, and like there's not necessarily an else for a while statement, but for a while loop, but you can work the positives in the while loop, and then the else statements, what you're trying to do, if not that while condition, you do outside of the while loop. I got to remember that.
Yep. The after the while loop, you are sure that you exhausted, the while loop condition. You exhausted that. You got through the end. And the key here is sort of to stop there. The problem on the other one was that we well, actually, was just that we detect if the next thing is null. With like line 54, we detect if the next thing is null, and if it is, then we just add a new node. But then that was giving us that infinite loop there where it kept adding 7. Okay. Questions or thoughts around this appending?
So append 2 is what you really want to do. Not my way. Not my way.
Your way is works fine as long as we keep the break there. But it's like break is something that we I forget about it sometimes, but it's something we could use.
Between that and like continue, I also forget that we can use continue too.
Yep. Yeah. And the also cool thing about continue is that it goes to the next loop, skipping anything after the continue, if there was anything after. But okay, cool. So this is great.
Can I share my code because I have one issue?
Sure, let's take a look.
Thank you.
Thank you, Ashia, as well, for sharing this.
This is what I got.
Oh, but I see you didn't change anything from the print.
Yeah, I just used it and I add this one in here.
Wait, but your append is still doing just what the print is doing. It's not creating the new node and adding it to the end.
That's the issue that I saw in here. Because here I see only 7 and then I just add in. So that's why like, oh, okay, now I got it. It should create a new node.
That's right, as Shias was doing. Create a new node and add it to the end.
Thank you.
Cool. Okay, so you're doing. I'm glad to see doing some operations on the linked list. There is. Let's take a 10-minute break. Let's take a 10-minute break, and then we'll see how we can do the same operations with a helper class that makes us just do the operations easier and allows for more flexibility. And that will be the linked list class. Right now we're dealing with nodes. And just remember that on LeetCode, on HackerRank, most of the linked lists that you're getting are this kind of linked list where they just give you the node that's the head to the linked list, and then you traverse it from there. Most problems won't give you like a linked list class. They just give you a node, and then they give you the head node. And your job is 9 out of 10 traverse that list to do something with it during the traversal. So let's take a 15-minute break, and then we'll take a look at that linked list class. Okay. I was not recording that last bit. So as I was saying, we're going to implement a linked list class and to hold the head, a tail, and the length. And why we want to do that is basically ease of use and keeping track of key information like the head, like the tail, the length. And also because we can have nicer methods and a nicer API to interact with our linked list. So we can have methods like add first, add last, add at index, contains, and other methods. And we could do the methods that we just wrote for our initial simple implementation of a linked list, we could have there as well. And this linked list will just be it will be sort of a wrapper on the concept that we already have. Yeah, where if we keep on that visualization, what we'll do is we will create a new linked list, like in this case, L equal new linked list. And then we could say LL that add first 3, and that will add the first node with that value. And the head will always point to the first node, which in this case is this box, and the tail will always point to the last, which is the last box, whatever that is. In this case, 6. Okay, any questions up until that point? Or thoughts? Oh, nice, you're all on camera. I can see all of you. It's good to see you. So let's do that. So what we'll do is maybe just keep down here. Let me comment this out. So we will have a class called linked list. And we have a constructor as always that we're not gonna initialize our constructor with anything or the linked list. We're gonna have a head. We're gonna have a tail. I guess I should initialize this to null. we're gonna have a length 0. And the point of this is so that we can do something like let L equal new linked list, and then we could do LL that we could do that append 1, and then we could do, let's do the same linked list that we had before, 3, 5, 1, and 6. 3, 5, 1, and 6. So this is a bit nicer on how we can add nodes to the linked list instead of having to do it manually like this. Or we did have the append function, and we're going to see how we can make this function faster if we keep track of the tail. So I forgot to also ask, what is the time complexity of that append that you just wrote? What do you think? What's the time complexity of that? Just unmute yourself and whatever you think.
I think it was linear.
That is absolutely right. It's linear because we have to loop all the way to the end of the linked list to be able to append it, right? So this is what we're doing there. This should be the same thing as we saw before. While we have a next, we just keep iterating until we reach the end. Once we have reached the end, our node will be the very last node, and that next node, we create a new node for it with the value, and we make it the next node. Cool. So, but once we implement our linked list, we'll be able to do that faster. Yes. So, well, I should have asked you also to do insert like in the front of the linked list. Insert in the front of the linked list, just so we see that first. What would we do if we had insert or add insert in front? And we have the same thing here. And this will add a value front of the linked list.
I guess you could say while node exists, see if there is a previous node, and if not, then add it there the same way we did at the end. So basically, if we kept the previous, so if we had while node, it would be while node dot previous exists, then you do node dot next. Wait. I'm confusing myself.
But actually, I don't want to let you go there just because we don't have a previous. That will be on a link and a double linked list.
Oh, okay.
Which we'll do for some other time. But let me actually drive a bit more here because this one is a bit of a mind shift. So if we want to insert in the front, let's say we want to do, you know how we did this here. I don't know why that didn't uncomment. Let me comment now. But if we want to do in the front, then if we do like insert in front, let's say we want to insert, so we want to insert maybe 3. No, 3 is already in the front. 2 in the front.
Do you
When
need
we print, yep.
right, would you need a loop? Because if you're adding to the front, you just need the head, right?
That's right. Yeah, so we don't need a loop. That's a good observation. We don't need to get to the end of the linked list. But it's a bit of a mindset because then in here we are changing what the head is. Because the head before was 3, right? If we print here, we have this. Append 7, append 7, and then after, wait, actually, we have just this. If we append 7, then we have 7 at the end. If we insert in the front, now we should have something like this. But this is a bit of a mindset here because what we're doing actually is swapping heads. We're swapping heads because the head before was 3, and now the head will be a new node. So the way in which we can make this function work will be we just create a new node the same way that we did before, new node with value. And then what we should do is just connect that new node to the rest of the linked list. So I'm going to say new node.next equal node. That will connect, that new node.next is our head. And then after that, I should return new node. So what this does is, yeah, this is in, what this will do is add a new node. So you can think of it as, do we have it here? No, like, yeah, no, I think I don't want to draw that. What we'll do is, this is something that we're going to see with the other one as well. I think probably we'll have time for one. But this creates a new node. It connects that new node to that new node's next to be equal to the node, which is our previous head, and then we return the new node. So that means that if we do here, we will need to have this is like the new head kind of thing. And here we'll need to do new head. Let's try this out. Let's run it. Insert, I have a spell mistake. Insert. Also, I think, I don't know why I have that. You don't need that console on there. Cool. Now we see that new node was added there. But because here we're doing that, we're actually swapping heads. Like we're just creating a new node and connecting that node next to be our previous head. So conceptually, yeah, no, I'm not gonna. I almost wanted to draw it there, but we're swapping heads. In fact, you can see that this might be a bit confusing, but if we try to do print n1, if we print n1, now n1 is no longer the first node in the linked list. N1 is the second node in the linked list. If we try to print n1, then I'm printing from n1 forward, but I'm forgetting everything that came before it. So that's why then for inserting, I will insert in front, I will need to return a new head. That returns the new node, and then we could just use that. Or I guess we could also do n1 equals new head, so that we can print n1, and we get the same. So we are overwriting the previous head. We're overwriting it now with a new head. Questions or thoughts? This also means that for inserting a node in the linked list at the end of the linked list, that's a linear operation. To insert a node in the front of the linked list or at the beginning of the linked list, that's a constant time operation. We're not doing any loops here. That's one of the advantages of linked list, that inserting in the front is really fast. It's constant time. It's the fastest you can get. Inserting at the end with our current implementation is a theory. With our current implementation is a linear time operation. So let's then take a look at how we could implement that. How could we ease some of that in here? So that when we append and we do ll.print, we could get the same thing. And I guess like we could also call this, let's call this push, so that it's like we're pushing everything and changing the head, as opposed yeah. So we could do, if we do append, we should get this. So let's implement this first. We're gonna, inside of the class, we could just declare a function called append, takes in a value. And then here is gonna be very similar to what we had here. Let me see. It's gonna be very similar. We could do actually exactly the same. Let's do this exact same thing, but we'll see how we can optimize it. I'm gonna copy even that. I'm gonna say here. Now I no longer have a node here, so our node is the head. So this that head that next. Oh, actually, you know what? For this, I should have let current node equal this that head, because I don't want to overwrite my head. And then we can just say, well, current node that next equal current node that next, and like that. So our append should be still working. Let's implement print so that we can verify it. And print will be actually exactly the same. So I'm going to copy it from here. And I think this have format document. Yes, nice. Oh, actually that didn't work. Sometimes it doesn't work. Wait. Oh. Cool. Okay, so now instead of our current node being that node that was being passed, now our current node is going to be this that head. And everything should still be the same. Well, this indentation is all off. cool. This goes here. Oh. Oh my goodness. I have a bit of an indentation. Oh, freak, I want it to be always right.
I think you're also missing a curly bracket for the while.
Mhm. Let's take a look. So actually, this is the wall for the while loop. And yes, this is okay. So I think we're good. Yes, we're good now. So let's try to print. Let's try to append first. And let's try to print. Also, let me comment this out here. Yeah. That on the linked list we can leave there. Cannot be properly next of null. Where is this happening? It's happening in the append. Node. Oh, right. I forgot an important step here, which is when we have our linked list empty, well, we need to check if it's empty. If it's empty, let's make our new node the head. So I should have checked that here. Let's see if here, let's actually do this. Let's write a function here is empty. Just checks return this dot length triple equals 0. If the length is 0, then the list is empty. So that will let us do if this dot is empty, then we want to make, okay, so I'm going to refactor here a little bit. Let's make the node first. Let new node equal new node with that value. This is going to be new node here. If it's empty, then we want to make the head equal to the new node. And we also want to make the tail equal to the new node because, you know, if a linked list with one node, then that means that that node is the head and at the same time the tail. Else, let's loop. Else, let's loop as we were doing before, and until we reach the end, and at the end we added.
I didn't understand the line 84.
84.
Yeah, for the tail to be a new node, is not going to be an empty. It's not, no, I'm sorry.
Say that again.
It's not going to be a null.
These two lines.
Yeah, and 84. I didn't quite understand the tail.
84.
Yeah.
That's because when we have, you know, imagine we have the container, which is divided into 3, right?
Yeah.
And this is going to be head,
And
tail, and length.
Yeah.
And that is 0. So what we want to do is we want to create a new node. And let's say that's going to be, I think it's going to be 3. And then we want our linked list, which is this box here, to keep track of that. So we're going to say, okay, the head, let's make the head point to that. And the tail, you know, because this is one node, this node next is pointing to null.
Yeah.
Right? But we should say that if there is a linked list with one node, then the head is that node, and the tail should also be that same node. Because this node is both the first node and the last node.
Okay.
Yeah, this node is when it's a linked list with one single node, then that node is the head and the tail at the same time.
Okay.
Mhm.
Thank you.
Cool. So that's why we do that there. Otherwise, if we loop until the end, yeah. Currently, O of 1, O of n, but can be O of 1. We'll I hope we have the time for that. Okay, so we should be able to append. Let's run it. So we got 6. We get 6, only 6. Current node is that head. Console log str. Maybe this is overriding. Oh yes, it is overriding. So I forgot to update the length, which means that we're always falling here. So in here, what we should do is make sure that that length, we increase it. We increase the length there. Okay, now we get back to what we had before. We have our linked list. This is a much nicer one because we can just do linked list that append and print in the method form without having those being separate functions. And let's do the append. Let's do the push, which is pushing in the front. So let's do push. It takes a value, same. And this is it is going to be a bit more evident. So actually, before we even do that, now that I have this visualization, so what we do, we're appending. The next thing we're appending, I think, is 1. Here the way in which the algorithm is working is we're saying create a new node. In fact, that node is created like some other different place with 1, and check if the linked list is empty. The linked list is not empty in this case. The linked list now has a length of 1. Oh, I cannot take that. The linked list now has a length of 1, so it's not empty. So what we do is we loop until the next element is null, and then we add our new node there. What that will do is, in fact, if I have this side by side, and I close this and I bring this here. When we have this case, when we have this scenario, and if I go back to my, where is, oh, no, I'm looking at the wrong one. If we look at our append, the linked list is not empty, right? Because now it has 1. So we don't set the head or the tail. What we do is we say the current node is equal to the head. So we establish a current node that is going to be pointing to this. And then we say, well, current node that next, current node that next, current node that next. We set the current node equal to the current node that next. In this case, current node that next is null, right? It's the null that we had here. So that means that we don't even go into the while loop. The while loop doesn't even run. Let me make it a bit more clear by having this in a separate line. We immediately just say current node that next. Oh, and here I just realized one bug in my program. We say current node that next. Current node is currently 3. That next is equal to the new node. So what that does is overwriting this null value from here and adding the next to point to 1. Now, the bug that I realized is that we should update the tail. We should update the tail to stop pointing at 3 and instead have the tail point, to the new tail now, which is the new node. There's a bug here on the append that we should fix. We could just do this.tail equal new node. To override that, so that we have, if we append the next number, I think we append is 5. What we do is first we create a new node with 5. Oh, that 5 looks weird. We create a new node with 5, and then we check if it's empty. It's not empty. Now the length is actually this seems to be an annoying bug in this program. The length now is 2. Then we do current node is equal to the head. And we say, well, current node.next, then overwrite current node with current node.next. That means that current node is currently 3. Then, no, why did they do this? It seems to be an update, actually. That piece is not even touching the other piece. Anyway, that we move current node to 1, and then at that point, current node.next is null. And then we say current node, which is 1, .next, current node, which is 1, .next equal to the new node. So that's we setting the next node to be 5. And then after that, we say this.tail is equal to the new node. This is so that we update. This is so that we update the tail to now point to this new node. And then we update the length to be 3. Okay, is that making sense?
Yeah.
Okay. And Joanna Siham?
Yeah, it is. I'm just a little confused with the if statement.
Oh, the computer changed it by accident.
Oh, thank
Yeah.
you. That was a good catch. Yes. Okay, cool. Okay. So then that's the way in which we're updating. In fact, I guess we could optimize this already. If we think about it, because we have, oh, now it's working as I want it. Maybe I pressed the wrong key. So if we think about it, we, instead of having to loop over the entire list to add the new node, if we wanted to add node 6, we start at the head, current head is that, and then if the next of that is not null, we just keep moving. So current node now is that, and if the next node of that is not null, we could keep going. So now current node is this, and the next node of 5 is null. So at that point we stop, and then we say current node.next is equal to the new node, and then we update the tail to be pointing to this. But instead of having to do that looping around, the way in which we can optimize the append is we already have the tail. So let's think about it in this scenario, where the tail is 5. So what we could do is just say, okay, we create a new node. We create a new node 6, let's say. we create a new node 6, and then we just say, oh, the tail that next is just equal to the new node. We say this dot tail that next equal to new node, and that will just make that link there, and then we can just override this here. Instead of having to go through the entire list, we could just use the pointer to the tail to do that. Does that make sense?
But how would we know where the tail was without that first initial iteration?
Because this tail here, this tail is always keeping track of where the tail is. We programmed it so that it's always keeping track of the tail, which is always going to be equal to the new node. So the way in which we can do that is, instead of this loop, instead of this loop, we could just say, okay, so there's a new node coming in. We already have a head. Then we can just say this that tail that next, the next thing of whatever the tail is. In fact, if we go back to the beginning, where we only had this, where the tail is pointing to, the same thing as the head. Here we can just say we want to insert 5, right? Or I think it's 1. I don't even remember now. 1. We can just say tail that next equal to the new node, which is going to be make that connection sort of here. And then we say the tail is no longer the 3, the tail now is the 1. And we could just say this dot tail dot next equal to the new node. And we update the tail, this dot tail, to equal now the new node. Or I guess we could even, that simplifies our algorithm a whole lot, and we will actually not need this line to make that tail the new node. Let's try this out just to make sure that it's still working. I'm kind of suspicious. Yeah, but we're still inserting. We still get our right result. And now here is where we discovered that appending to the end of the linked list, if we have a tail, it's a constant time operation. We don't have to loop, because when the next number gets inserted, we're doing this here. We create a new node, which is, let's say, 5. And then we just say, we check if it's empty. It's not empty. It has already 2. It has 2 elements at the moment. Then this dot tail dot next, make the current tails next, the new node. The current tail is pointing to 1. So that 1 dot next is going to be equal to the new node, which is 5. And now we update the tail so that it's pointing to 5. Does that make sense?
Yeah.
And then we're saving us that looping that we had on the other one, which is okay. It's okay, but this is just nicer and faster if we keep track of the tail. Now let's see. So that's the append. Print still works exactly the same. Push will be similar to the other one, where we actually this will be exactly the same. We create a new node, we check if it's empty. If it's empty, then we make both the head and the tail that new node. Otherwise, we want to overwrite the head. So it's exactly the same as the other one, but now with the head. This is that head wait, hold on, let's see. This is that head. Now we should say new node that next is equal to this that head. This that head now is equal to the new node. And with this, what we're saying is, let's say we want to insert 2. So we create node 2. That's a 5. We create node 2, and then we check if the list is empty. At this current point, the list is actually 3. So then we say, okay, the new node next is going to be the head. So that is the new node next equal to the head. The head is 3. So then we connect that here. And then we say, okay, now my new head is the new node. So overwrite the previous head. So now head stops being, that. And now head is pointing to 2. So let's try this one out. Let's try that push. Oh, I also forget, push should also increase the length. So now we'll have an issue there. Let's try LDL that push. So pushes will be pushing in the front. Let's push 2. Now and let's print in 2 places. If we print here, we should get 2. We should get this also. This is, I'm never appending 7, so I'm just gonna remove 7 from there. Because in my appends, I never append 7. But if we push, that push should go in the front. Let's try it out. There we go. We have now 2 in the front, and it's happening exactly as I drew it out here. How does this sound?
Good.
So this is now, you might have heard me say, the best way to implement a queue is with a linked list, because it's constant time to add at the front, or to actually, it's constant time to add and remove from the front actually, and it's constant time to add or remove from the back as well. Even though we're not removing here, it's constant time to, in this linked list right now, it's constant time to add the tail, which will be at the end of the queue. And it will be constant time to remove from the head. In fact, if we want to remove, like, we could write that in a minute, which will be remove, let's call it remove head, or remove first. Remove the first node. What we could say is let's store it first. Let's say removed head is going to be, this is that head. And then we say this that head is equal to this that head dot next. And then I guess we should say this dot length minus. How about this? How does this sit? And I also forgot that we should return removed head dot vol.
So why are we returning the value if we're removing it?
Yeah, just because like you may want to get the value back. If this was if this now we can use this linked list as a queue, and it will be efficient because it's constant time to remove from the front of the queue, which is removed from the front of the linked list, and it's constant time to add at the end of the linked list, which will be adding at the end of the queue. This is removing just because when you remove something, you most likely want the thing that was removed. That's why it's returning.
Okay.
So for instance, if we now say let removed element equal ll that remove first, and we do ll dot print here, and we say console log removed element, let's see what we get. So we see that this was the linked list before. We remove the first element, and this is the linked list after. And this is the removed element. So removing from the front of this linked list is constant time. We don't have to loop. And the same will be true if we remove it from the end. Wait, let me see about remove from the end of the linked list. Actually, remove from the end of the linked list, we could make it constant time. We could make it constant time, but removing from the end, we will need to loop on until we get the node, before the last one, so that we can set that node next to null and disconnect the tail, and then make the new tail that second to last node. So we'll need to loop that there. The removing at the end of the linked list will be linear time. It could be linear, but it will require a previous reference. If we have a previous, then we can make it in constant time. Questions or thoughts on everything we just saw?
So I'm trying to, like, I have the print, push, print, but it's not showing me that second line. So the 3516 and then the 23516, it's not showing me that. But it shows me the removed element is 2, and then it shows me 3516, but it's not showing me that print after I push the 2.
Do you have this print right after the push?
Yeah.
There might be a bug then in the print or in the push.
Okay, let me check the push. Okay, so I have let new node equals new node, takes in a value. Then it says if this dot is empty, set this dot head to new node and set this dot tail to new node, else new node dot next is set to this dot head, and then this dot head is set to new node, and then outside of that, this dot length plus plus. Maybe it's my print.
So let's take a look at the print. One thing that I changed in the print was just this: the current node is going to be the head.
Okay, this dot current. Okay, current node equals head, and then I have my string, and then I said while current node, and then and then I said not current node dot next, new string plus equal current node dot val, else new string plus equal current node dot val plus the arrow. Outside of that, current node equals current node dot next, and then lastly you return the string.
Oh, I am console logging here
Where?
in the last line of print.
Oh, you don't return the string? Okay.
Yes, I don't return a string. That might be why.
Okay, let's see. Yeah, that was it.
Awesome.
Okay, cool.
Cool. So then, do we get to see how, like, the utility of having this other class? Like, why would we let me ask this question. Why would we have a linked list class? Why is this good?
Is it because it allows us to add other functions, I guess?
So yes, it allows to have methods so that this reads a little bit better, saying ll.append, right? Because before we had to pass like the head node. We on our initial append here, we had to do this append n1 and then 7, which is kind of is a bit, you have to do a little bit more thinking here, like where is 7 being appended to? It's being appended to n1, but in here is like, you know that 5 is being appended to ll, which is the linked list. So that's one good method, one good reason, because you have methods in the class, which makes it more readable. This is what we will call a nicer API. It has a nicer way of interacting with the linked list. Any other?
Also because you could have like everything you have in the constructor, like the head, the tail, and the length.
Mm-hmm. That's right, because this is very useful information to have at all times. It's useful information to know how long your linked list is without having to count every time. You can just check the length, and that will give you the length of the. Let's see, if we did this correctly, we should get like console.log ll.length 4. And that was constant time, you didn't have to loop. Also, having a head and a tail allows us to append the head in constant time and append push is adding at the head and append is adding at the end. And those are constant time operations because we're keeping track of this head and tail. We saw that when we don't keep track of the tail, as we were doing in our initial append or push, we will need to loop all the way to the end to be able to add that node all the way at the end. In here, now we just grab the tail and say, oh, the next tail of the tail, we already know that the tail is the very last thing. Make that the new node. And make that new node the new tail in here. So those are the advantages of having this linked list class. As I said, like if we do, if you go in libcode and we were to like problems linked. If we were to go to linked list, let's see. Yeah, one of the merge to sorted linked lists, remove duplicates, let's say. when you go here, you see that here you just get the head. So you don't have those nice methods we were building. You don't have like append or push or print. They just give you a node. This is a simple node, which is going to be the head, and they tell you this is what a node looks like. Has a vol and a next. And you have to then, in this case, remove duplicates from a sorted list. This should be able, this we could do in linear time. And just so we discuss it, we're not gonna write it, but because we're already over time. Oh, way over time. Here, if the linked list is sorted, if you know that the linked list is sorted and you want to remove duplicates, what will you do? Any ideas? Sure.
Maybe do a count and return the keys of the counts.
We wouldn't need to do a count though.
That's doing too much. Okay, maybe.
No.
Okay, maybe. Maybe you traverse through the list, and if does it have no? Okay, so you traverse through the list, and if the current node is equal to the next node, you're going to delete the next node.
Okay, let's do it if we want to do it.
Or delete the current node and then move on to the next node. And then you'll see again if there's another duplicate of that same one again, and then you'll do the same thing. So you'll delete the current node instead of the next node.
So I guess we'll do, well, current node that next actually. This is a while. If current node dot vol triple equal the current node next vol, which is what you said, right? Then remove current node next, right?
No, not current node next, because we have to be able to continue through the loop. So you want to delete current node.
Okay.
And then set current node equal to current node dot next, so that it's constantly moving through the loop. Because if I did it the first time where I remove the current node dot next, then I have no way to continue after the next one that I deleted.
Yes, but there is a way to continue, which I think what we'll do conceptually is we'll jump over, basically. So if we're looking at one, and then we check the next, and we see that that's the same. What we can do is say, okay, this one's that next. I don't want it to be the duplicate next. Let's just jump over so that the next of that is equal to this.
But what if you have 3 of the same numbers?
If we have like 3, 3, and 3.
Yeah, you're going to jump to the same number. So you would have to do it again anyway.
Oh, that's a good point. Let's see. If these are the same, I was saying, we'll jump over here. And then that ends up being just the same as this. And I guess in that case, we have to keep checking. Actually, we'll need to sort of keep checking until the next of whatever current there. That's a very good point. Until the next of whatever current node we're on is not equal to the same value. So, let's do this. Current value that if that is the same, then we want to keep looping. We want to loop again as long as as long as these are the same. Well, I guess maybe we can then get rid of the if statement. We'll see. Making. Oh, so maybe we should have like sort of a next node. I think that would be helpful. Yeah. Set let next node equal current node dot next. Just so that we could then say next node, and we can keep advancing next node. And I think we're going to get rid of this if statement. So if the current value is equal to the next node value, while that is true, we just keep going next node equal next node dot next. So that, I think that will solve this issue here, where we are comparing these two. Oh, forget that. If I'm annotating, I have to be here. Oh. If we're on this example, I'm sure this is going to be one of the test cases. We're here, and this is next. This is next, and this is current. We're checking while current node that next is the same value. We just move next to the next node. So then, in this case, the current and next are the same. So we just move next to the next node. We erase this. And then here, next, current next, that value is the same as current next. As is current node, that value is the same as next node value. So then we move next to null, kind of thing. We move next, now next is null. And then there we'll actually have to watch out for this case where we do current node dot value, which is 3, equal to current node dot value, but the current node is null. So that's going to throw an error because it's going to say cannot read value of null. So we need to watch out for that. To handle that, I guess we could just say well, next node. Well, we have a next node, and the current node of value is equal to the next node value. Then let's keep doing that. As soon as we break out of this loop, which will be in this case. In this case, the next node will be. In this case, the output should be just the node 3 because we removed all the duplicates, right?
Mm-hmm.
So we should just do as soon as we break out of this loop, we can say current node that next is equal to whatever next node ended up with, which will end up with null here. If we go back to our original example, here, we are checking this too, and we're saying if they're the same. Actually, let me get rid of this if statement now, because this is the same if statement as the while. The while already takes care of that. While we have a next node, and while current node value, which is 1, is equal to the next node value, which is 1 as well, then move next node, which is the second bar. Just should have labeled a bit better. Let's do this. Current and next. while they're the same, then move next node to the next, which then ends up moving in here. And I will erase this. And now at this point, our loop will break because we do have a next node, but the current node, which is 1, is not equal to the next node value, which is 2. At that point, we break, which then we make the current node, which is 1, that next be equal to the next node. So then that's sort of jumping over so that the next node is here. And then does it have to, I think this might be it. Here.
You're missing a T on line 16 for next node.
Line 16. Oh, thank you. Yes. And what should we return? Delete all duplicates such that each element appears only once. Let's return head. Let's try to run the code. Oh, actually, this is we got into an infinite loop. Any ideas as to why? Time limit exceeded.
Next node.
Say that again.
Should it be while next node dot next or no for line 15?
Line 15, next node dot next. So we already kind of have that with this next node here. I think what you're pointing at is that we never move current node, which we should also move, but only under. Yeah, here we need to move current node.
But current node dot next is already next dot node.
Yeah. So then I guess we could just do current node is equal to next node. Because the infinite loop is just that we never move current node.
Okay.
Let's try that now. Okay, we got the first case. I think we could actually even write our own. So let's try this one. And this throws people off a little, like a lot actually. The fact that I'm writing this looks like an array, but it turns out that how LitCode works is that, yes, this looks like an array. LitCode will look at this and then make a linked list out of it. It's not that we're feeding an array here, we're feeding a linked list, we're feeding a head. So let's run with this. This should return a single node. Oh, we got a problem here. Cannot read next of null. So if I try to submit, then there is some cases that it's not going to pass, because I'm sure this is one of the example cases. Yeah. So let's think about this. Also, feel free to drop from the call if you have to go, because that's more than understandable. Current node up next. Let's see. Let me go back. Here. Well, I also not sure about, yeah, we're returning the head. This is crashing there. So this is the scenario where it's crashing is where we make current node, which is this scenario with the 3 threes. We make current node, we make it jump to that next. Current node that next is going to be equal to is going to be equal to then null, because we're in this scenario where current node is at 3 and the next it already reached the end. So we say current node dot next is equal to next node, but next is already null. So we're saying 3 and the next of 3 will be null, which is what we want really. But then we say current node is equal to next node, which is null. And then we go back to the while loop saying, oh, and I think this might be something that I should have brought out also. Maybe I didn't understand. Here, we're checking if there's a next there, but there's no next of null. So let's just do, well, current node. Let's try that out. Let's run with our example. See what we get. Okay, so with that example, we are expected 1, expected only 3. Let's submit. Let's try to see. Okay, what is this? Next node. Cannot read next of null. So this is that I'm forgetting some of the edge cases. But I imagine, oh, you see here, you were fed, our algorithm was fed an empty list. So we have to guard for that. So we should check here, if not head, turn. Probably that will take care of that case where there is no head. Those are all sort of edge cases you should watch out for. Output undefined. So we're still on the same. The input was an empty list. Our output was undefined, but this was expecting an empty list. This is confusing. Let's just try to return, if there is no head, let's try to return the head. Because return by itself will return undefined. There we go. For some reason, that one there is like very confusing, because it's like, maybe it's return null. Let's see how they consider that. Oh yeah, that's like a tiny thing, but could throw us for a loop. When I do return, my function will return undefined, which is something that they don't like. Just the test cases here, that they're saying our input was an empty list, our output was undefined, but they didn't like undefined. They were looking for null. So I guess the empty list is just null. Okay. In here we just do return null or return. Yeah, return null is better. On the head, because the head is null. Cool.